Hello and welcome to episode 2 of Science with Shinrai Sensei in our series of Better Together with Shinrai Sensei. Today we are going to be talking about matter. Why does it matter? Well, matter is anything that has mass and occupies space. Now, having mass is a measurement that typically here on our planet we use as a measurement of weight, but in its purest form, mass is not about weight. It's about the number of particles that make up an object and how large those particles are. So really, if you want to accurately understand the mass of an object, you need to first understand the mass of the molecules that make it up. So on the periodic table, right, the mass of individual atoms is what we call their atomic weight, is what their mass is on their microscopic level. And so the numbers that we use to convey mass for the periodic table are how we organize the periodic table. So hydrogen is 1 because it has an atomic weight of approximately 1. Helium is 2 for the same reason. The atomic weight is approximately 2. And so on and so forth. Lithium, all the way through. So you have the atomic weight is really the mass on the atomic level, which is very minute, right? So once again, like I said, if you were really trying to find the mass of an object, you would be looking for how massive every part of the object is. In order to understand its true mass, you have to understand its makeup. But like I said, here on Earth, we say that we're measuring mass, but really we're measuring the gravitational effect on the mass. So it's more of a weight than it is a mass. Hence why you have to use scales in order to measure mass. But matter, as is written up here, has mass and takes up space. So if it's matter, it has to occupy space as well. Now, I'm not really 100% sure as to what things have mass but don't occupy space, other than the extremely theoretical dark matter, which, like I said, extremely theoretical. There is no proof of dark matter outside of the mathematical expressions and equations that they have used to prove it on paper, but you can abstract nearly anything if you are determined enough and you can institute enough variables that you can't actually find values for. I can make anything work. So I can write a mathematical equation that would make 2 variables equivalent before I reveal to you that the variables are not equivalent. So, simply put, just because you can do it on paper doesn't mean it's real. So, like I said, I'm not really sure what things have mass and don't take up space, but yeah, we define matter as something that has mass and takes up space. Alright? Now, when we break down matter to its simplest parts, the smallest unit of matter is an atom. Now, the reason that it's the smallest unit is the smallest cohesive, coherent unit. It is the smallest unit of something stable enough to be matter, right? So you have like subatomic particles called quarks. You have the subatomic particles, these 3 subatomic particles that are made of quarks, by the way, that make up the atom, right? These 3 all make up an atom. And they're all 3 made of quarks, which are even smaller than what all 3 of these are. And electrons, if you don't know, are extremely small, to the point that even observing them is a feat unto itself. So the fact that we know that they are made of subatomic particles that are even smaller than electrons, called quarks, is something we couldn't have possibly known when we came up with the term atom, because the term atom was always meant to be like the most minute part of something was when it was atom. So when you say something was atomized, it was reduced down to its last atom. You know, you're basically saying it's reduced to its finest part. Now, the atom being the smallest unit of matter, well, now we also understand that the atom is made up of different parts. You have the proton, the neutron, and the electron. And the proton and the neutron, I will underline in red, because these two make up what is called the nucleus. The proton and the neutron can be found in the direct center of the atom. And so these two subatomic particles are always going to be found in the center of an atom. So the proton represents a positive charge. It is a particle directly in the center, positive charge, right? Neutron is a particle directly in the center, right alongside the proton, that has a neutral or no charge, right? And these two particles make up the nucleus, which is the center of the atom, made of protons and neutrons. All right? Pretty simple so far. Now the electron is where things get a little complicated, and the electrons are probably single-handedly responsible for a lot of the more wild theories in physics. But that's beside the point. So the electron is a negative electric charge, and it's a super, super small particle. In comparison to the protons, the proton, usually when you're looking at like the periodic table, right? So the periodic table, the atomic weight of a atom of a certain, element, right? So the atomic weight of an element is almost exclusively because of the proton. So if you look at the atomic weight, the whole number that the atomic weight is, which is largely how the organization of the periodic table is made, the whole number of the atomic weight is exclusively the nucleus. The nucleus makes up the entire whole number of the atomic weight of the particles that you're going to find, of the elements, single atoms, right? So hydrogen atom, 1 is the atomic weight, unless it's a ion of it or a alternative version of hydrogen where there's some nucleus expansion through adding of neutrons and such like that. So a pure hydrogen atom is a proton, single proton, with an electron orbiting in it. And that's why a hydrogen has an atomic weight of 1 point. I don't know the exact decimal off the top of my head, but it's a 1 and a decimal, right? And that really, 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 really small decimal that follows that 1 is the value of what the electron brings to the atomic weight. So electrons represent a fraction of a percent, or a percentage or a fraction of the value of the atomic weight of an atom. Whereas the proton and the neutron are going to make up the vast majority of the atomic weight whenever they're present in an atom. Right? So the electrons, they are super duper small, and they also orbit in different ways, right? So it depends on how many electrons are present, and it also depends on the other particles that they're around, how exactly they orbit the nucleus, right? And so when you get to having larger atoms or molecules, the electrons really behave so randomly that you can't directly observe the location of an electron and its speed at the same time. That's a principle in physics. And you can't measure, obviously, its speed and then know its location at the same time. So electrons, even though we like to have these nice, pretty little pictures, right, that show an atom being this nice little solar system diagram, right, which not even the solar system abides by. You have atoms have this nice little solar system looking thing that the electrons just sit in a nice, clean, pretty picture orbit. And they stay in that orbit all the time, just perfect circle rotating around. Well, in actuality, they're rotating in kind of random directions, and so long as the center of that orbit remains the same, the only thing that remains the same is that they will remain the same distance from the center of that, unless for some reason the electron is attracted away, at which point the atom will have a charging to it, where it has either a positive charge or a negative charge or something being given to it because of having less or more electrons based on whether or not electrons get stripped from it, right? But as I said, we like to draw pictures of atoms with these nice clean little rings around them, showing where the orbits of, you got the nucleus here with like three protons in it and no neutrons, and then the electrons are sitting in this nice little thing where they just do, and they're sitting there. Well, that's not how they stay in all reality. They move around because it's a three-dimensional space that they're moving in, so they're constantly moving just random directions around that nucleus. And so long as that nucleus is always going to be the same charge, and so long as nothing comes by to strip an electron away, then the electrons will remain in that distance away from the nucleus, but they'll never be on just a set orbit. All right, so if you guys need to, you can take a screenshot of this at any point in time, but for now I'm going to erase this and we're going to move on to the next subject, which is going to be physical chemical properties and their changes, right? All right, so there's matter and why it matters. I love puns, right? So erasing this all off. Now, when it comes to materials, right, you have, metals and every other, metals and liquids and, gases and stuff like that. Well, they all have physical properties and chemical properties, right? So, some properties that they have here. Malleability. Magnetism. Boiling point. Melting point. And solubility. Right? So, malleability equals ability to be markers die, pressed or flattened, which, I mean, you'd kind of think that pressed and flattened would be the same thing, but I suppose not in their mind, but in my mind it would be. Right? Magnetism. I'm going to use green because my green marker is not dying on me. So magnetism is whether or not something has electromagnetic properties. Because the definition they give is whether or not something is magnetic, which is using a definition to define a definition, which anybody who's ever taken a basic English course will tell you you don't do. You never use a definition, you never use a word in the definition of the same word. So if I say, what does a magnet do? You can't say it magnetizes things. It just doesn't make sense. It's kind of silly. So we're going to go ahead and work around that one. All right, and boiling point is the point, the temperature at which liquid becomes gas. Temperature, or melting point, the temperature at which solid becomes liquid. Now, solubility is anything's ability to be dissolved in water, right? Can be dissolved in water, right? All right, now let's go over these a little bit more. So malleability is pretty easy to understand, you know. Think about the difference between a stone and some clay, right? A stone, while I'm sure under the right conditions and the right temperatures and the right amounts of pressure, you would probably get a stone to be malleable. The clay at room temperature, and so long as it's, you know, kept with the right amount of water content, and so long as it's not baked or, you know, left out in the sun to dry out, clay will be malleable. Okay? So like I said, you know, a rock versus some clay. The clay is going to be malleable. The rock will not be. Now you have magnetism. Magnetism, contrary to what the book says about things being magnetic, well, electromagnetic charges are a thing. Okay, so magnetism in and of itself is not a separate entity from electricity. So if something's electric, it's usually going to have some level of magnetism as well, and vice versa. If something is magnetic, it's usually going to have some sort of electricity as well. Now, whether or not you can use that electricity, or if it's in a way that, you know, if there's a way you can harness that electricity from the magnet, then you can do that. But usually the magnet, being magnetized, is a form that the electricity takes, right? Because the electricity is what's maintaining the polarity of the particles in order to maintain their magnetism, right? Because magnetism is all about polarity of particles. It's not about this mystical, magical thing that attracts two things together that are, you know, iron. It's just a principle of electricity. And that's why electromagnetism is a thing. This is why we understand electromagnetism is its own entity. Electricity and magnetism are intrinsically linked. So, magnetism is also about electricity as well as magnet. You know, I'm not even sure what the adjective version of magnet is, but we'll say, you know, magnetism, I guess, would probably be the best way to put it. So, electricity versus magnetism, there is no versus there, they're the same thing. So, magnetism is whether or not something has electromagnetic properties or the capability to have electromagnetic properties. Now, whether or not something can be magnetic and magnetized, that's different. When it comes to electricity versus magnetism, they both have different things that they work on better, right? Electricity, you know, electricity cannot affect certain things that magnets, perhaps, you know, magnets could. Or electricity can't do certain things that perhaps magnets can because of the nature of what they do, right? But magnetism is all about generating a north and south pole that attracts or repels depending on the polarity of the object as well. So, have you ever taken two magnets and if they're clearly marked like north and south, right? You ever try to push the north and south pole together and you're sitting there and you're watching and you're just, and then you can get them like super close together. And sometimes if they're really weak magnets, maybe you can get them to actually touch. But if they're not weak magnets, you're going to sit there and you're going to push and you're going to push and you're going to push. And the closer you get together on that magnet, the harder it's going to repel you getting those two magnets to touch, right? So, magnetism attracts opposites. Pretty basic, okay? Now, the boiling point and the melting point, very simple. There's also a term that they don't mention in here, but a term we'll go ahead and put on here just the same. Sublimation. Okay? Now, every substance you can think of has a boiling point and a melting point. But every point you can think of also has a sublimation point, which is going from solid directly to gas. Okay, so typically with there are 4 stages of matter, which I will also go ahead and write up here with my functional red marker. So, matter is solid, liquid, gas, plasma. Okay, I think I better angle this camera just a little bit down so you guys can read that little bit on the bottom there. All right, cool. Now, so you have solid, liquid, gas, plasma are the 4 states of matter in the universe. And the law of conservation of matter states that matter cannot be created nor destroyed, simply transformed. Okay? Now, let's explore that and explore why these 3 temperatures are important. Okay? Every single element has its own melting point, boiling point, sublimation point. As far as plasma goes, plasma is it's basically like an electrified gas is the best way to think of it, right? But it's not really necessarily 100% accurate to call it that, but that's the closest that we can come to saying what a plasma is. Plasma is actually, contrary to what you might believe based on your experience in everyday life, plasma is the most common form that matter takes in the universe. because plasma is what makes up stars. Because the stars are operating at extreme heats and extreme charges. Stars are the largest magnets in the entire universe, outside of perhaps black holes. So, but stars pump out massive magnetic fields that have, in some cases, light year sized effect zone, areas of effect, right? These magnetic fields are so massive that sometimes an entire solar system can fit within a magnetic field of a star. Our magnetic field for our planet is large enough that we can usually be comfortably within it when we have like satellites that are able to be in geosynchronous orbit and not come down, come crashing down to Earth, but are also able to, sit up there and not move. From our perspective, not move. They can stay at an altitude that prevents them from, coming back down to Earth, but also be at a low enough speed in correlation to the rotation of the Earth that they can seem to remain motionless from the perspective of the planet, even though they are moving at hundreds of thousands of miles an hour. So, the largest magnets in the universe are being generated because of plasma, which is where that electromagnetic charge creates a environment with the atoms that are within that electromagnetically charged plasma. The environment that they are in is so electromagnetically charged that they generate heat, they generate light, and they generate magnetic fields. And these magnetic fields can alter the direction of objects around them. So you can see, like, if a meteorite or something like that, if an asteroid is made largely of metal and an object with a magnetic field passes in the vicinity of that asteroid, you'll actually be able to watch that asteroid move in an attraction to that magnetic field and be dislodged from its orbit. And in fact, we see this very frequently with objects that pass by Jupiter and the like. It's not just their gravitational fields, it's also their electromagnetic fields that cause the phenomenon that we witness when we see objects being attracted to them or being repelled from them. It is no small part because of their electromagnetic charge, as well as their gravitational force. The gravitational force we give far too much credit. And if you talk to anyone that's an actual astronomer, gravity is one of the weakest, quote-unquote, forces, because as we understand it in Einsteinian physics now, gravity is not a force. It is more so an effect that we feel than it is a force. I think is the best way to put it. All right. But anyway, back to the topic at hand. So you have 4 different states of matter: solid, liquid, gas, plasma. Plasma being the most common in the universe. Well, between these 3, right, it's a matter of temperature. Between solid, liquid, and gas, it's a matter of temperature. So, I can have, really, if the temperatures are high enough and the density is sufficient, I can have, if the density is low enough and the temperature is high enough, I could have a gaseous form of iron, right? And this isn't just from like having superfine particles of iron from like somebody sanding something with iron on it or something like that, or grinding something down with iron on it. No. In this case, we're talking about legitimately having, at a certain temperature, iron would enter a gaseous state. Now, the gaseous temperature of iron, the boiling point of iron, well, that's a very high temperature that we don't have any real reason to do that, has a boiling point. So everything has a boiling point. Every element on the periodic table has a boiling point, a melting point, and a sublimation point, right? But the sublimation point's a little bit trickier because you basically got to take something and you got to keep it well below its melting point, its melting temperature, right? You've got to keep it well into the freezing temperature for that element. And then you've got to suddenly take it really quickly out of that environment and bring it into an environment where it is well above its, you're keeping it well below its melting temperature, and then you suddenly bring it into an area that is well above its boiling temperature, right? And this will also bring us into a discussion on, I don't remember the name of the principle, but there is a principle that basically states that just because you're, just because you are heating up the container that a liquid is in, the liquid can never be above the temperature that is its boiling point, right? So the same thing would then go for a solid being taken out into a temperature where it will become a gas, right? So I take that solid, I bring it into an area that should make it into a gas, temperature-wise. It'll skip that liquid point altogether and go straight from a solid to a gas. Think dry ice, right? Dry ice is the quintessential example of when you want to make an example of sublimation. Dry ice is the quintessential example that everybody uses. And dry ice is often used in like movie effects to make low-hanging fogs that obscure the ground for scenes where somebody's walking through a graveyard and you want to make it really, really atmospheric, right? You would use dry ice because of its sublimation point. It will create this smoke look before the carbon dioxide that makes up the dry ice, right? The carbon dioxide of the dry ice will eventually dissipate into the air, but it's heavier than much of the air around it, one, and two, it is also in such a concentrated form that as it's sublimating, it is so concentrated it's just hanging together for a little bit before it just goes and blows away, right? But the boiling point, no matter what temperature the container that you are using reaches to boil water, right? This is the principle that I was talking about earlier. No matter how hot the pot that you boil the water is, the water will never be above 212 degrees. Unless you or whatever the boiling temperature is for the environment that you're in. Because air pressure, or just generally pressure at all, determines boiling point. I can actually boil water at you can get water to boil at below what we would consider freezing temperature if you put water into a vacuum, because then the vacuum, due to the nature of diffusion, right, which we will talk about as well later, but I'll kind of introduce you to diffusion now. So if I was to have a glass of water, right, that is being kept in a refrigerator at 35 degrees Fahrenheit, or 1 or 2 degrees Celsius, it's not frozen, but it's getting close, right? Then I put it in a chamber to remove all the air pressure from the chamber. I put it in a vacuum chamber, and I simultaneously, as I'm putting it in the vacuum chamber, I also reduce the temperature in the vacuum chamber to, let's say, -1 Celsius, or like 29, 30 degrees Fahrenheit, right? You'll see that as the air pressure drops, despite the fact that the water initially looks like it's going to start freezing, as the air pressure drops, the water is going to slowly disappear from the glass. And while it may not look like typical boiling, because of the fact that it is not, it's not necessarily heating up from the bottom or the edges or something like that, and the heat's coming from the outside and making the water in contact with the surfaces vaporize, and then the vapors have to travel out of the water. It will actually vaporize from the top because of the fact that it is not boiling because of temperature, it is boiling because of pressure. So once again, boiling point and melting point are also extremely dependent on the pressure that the environment is and the temperature that the environment is. These two go together very intensely when it comes to melting point and boiling point, right? And so boiling point, like they'll ask you, how many feet above sea level are you? Knowing how many feet above sea level you are tells you how much higher or lower the boiling point is for you, if you know how the barometric pressure works and how barometric pressure changes the boiling point, and like how many degrees off, right? But at higher altitudes, the boiling point is lower than at lower altitudes. The temperature you have to boil water at, 212 degrees Fahrenheit or 100 degrees Celsius, right, is not the same. It is, at sea level, it's 212 degrees Fahrenheit, 100 degrees Celsius, but above sea level, that temperature drops. So there we go. We got done talking about boiling point and melting point, right? And sublimation, as I said, is going straight from gas to or straight from solid to gas, right? Now I know there is a converse of, or an inverse of sublimation. Can't think of it off the top of my head. I'll look it up sometime and give it to you guys, but sublimation for now is what we'll focus on, and we'll focus on the fact that you're going from a gas, or you're going to a gas from a solid. You skip the melting point entirely, yeah, and you go straight to the boiling. You go straight past the boiling point with a solid, and you'll see sublimation. Okay, and then finally, let's talk about solubility, right? Now, solubility is more for chemicals, and not atoms or specific elements, but more for mixtures of elements that we see every day. And solubility is whether or not they can dissolve in water, right? So almost any salt, which by the way is the combination of an alkali, I think it's alkali metal and halogen, which is where chlorine, fluorine, and stuff like that come from. And alkali metal is where sodium comes from on the periodic table, right? So any combination of those two, I want to say they're called columns, and then it's periods this way, but we'll get into that in different episodes. Any combination of the elements from that. So sodium chloride is the most common one that we know because that's table salt, right? But if I make, potassium chloride or something like that, which is also a very common, it's a very common salt substitute. So if you see like no salt from Norton brand, like the no salt in the white shaker with the vegetables and fruit and stuff like that displayed on it, and it says no salt, if you read the chemical compound that it is made up of, it is potassium chloride, because the sodium raises your cholesterol. They decided to substitute it with potassium, and the potassium and the chloride make it more soluble in water and make it able to be absorbed by your system, right? Because pure potassium is highly reactive with water, right? That's the characteristic of the alkali metals and the alkaline earth metals. So the alkali metals all react highly with water, and alkaline earth metals all react not as strongly as the alkali metals, but still very strongly with water. Like if I throw pure, I throw a little thing of pure sodium into a bucket of, 5-gallon bucket of water, it will generate an explosive reaction. So these things need to be put into compounds that make them more let's say, friendly with water in order for your body to be able to use them, right? But for now, we'll say these are some basic physical properties of things, and whether or not you can, see them. And let's get into a little bit more of like chemical properties, right? So, and if you guys want to keep that for notes purposes, please take a screenshot of the screen, rewind back to where it was at, and take a screenshot of the screen, right? Otherwise, it's gone. And just like that, I'm magic. My eraser's getting kind of dirty. Alright, so chemical properties, you have flammability and reactivity. Okay, so you have flammability. And reactivity. At least it's according to the book that I'm using. Now, let's go ahead and make an important distinction here. Right? Flammability does not equal combustibility. Right? Flammability and combustibility are not the same thing, because combustion does not always mean a flame. It very typically means a flame, but a combustion is a reaction. According to chemistry, anyway, combustion is a reaction that consumes oxygen, right? So anything that consumes oxygen is technically combustion. So cellular respiration is a combustion because the oxygen needs to be consumed by the energy releasing reaction that your body uses for cellular respiration. Your body, uses oxygen that it breathes in to break apart carbohydrates into a form that your body can then use that energy. And that's how cellular respiration makes, and this isn't just for your body, this is for all cells everywhere. Everything that is alive uses cellular respiration to generate energy. There's alternatives to cellular respiration, but it is the most efficient reaction for them. But combustibility is a chemical reaction with oxygen, whereas flammability is simply whether or not something lights on fire. And something can be flammable, but not necessarily be combustion. So flammability and combustibility are not the same thing, even though they have a huge area of overlap. They are also not. It's like a Venn diagram, right? Just because there's an overlap doesn't mean everything's in those two circles. Just because they overlap, those two circles don't mean the same thing. They're not the same thing. But flammability is the ability to light it on fire. Combustibility is about an oxygen reaction. And then reactivity just means whether or not it reacts to a stimulus of an input of stimulus. So like an input of energy of some nature, reaction, and then this says oxygen, but that's a combustion reaction. So combustion reactions are, I guess reactions, but combustion as its own word in chemistry kind of defeats the purpose of just having a reaction. But I digress. I'm just going based on what my book is telling you. I'm trying to, learn a little bit more myself, but also help you guys to learn. And I'm also trying to correct things that I find in here that, or simplify things, I should say, that I find in here that are kind of a little odd. So you have, for chemical reaction stuff and chemical properties, you have the concept of a chemical change. And the chemical change means a new substance with new properties. Excuse me. So think sodium plus chlorine equals sodium chloride. All right. Sodium and chlorine added together is a chemical change that changes the property, because chlorine is very, very reactive to many other elements, and they especially don't like the noble gases, right? Chlorine, fluorine, and such do not like noble gases at all. But when you combine sodium, which is highly reactive with water, and chlorine, which is highly reactive with noble gases, you get a rather inert substance or non-reactive substance known as sodium chloride, which is then, in our case, able to be consumed and used for seasoning, but also is very necessary part of our lives. Your body requires a certain balance of sodium in it at all times to help it to retain fluids so that you don't dehydrate. If you don't have enough sodium in your system, then your body can't absorb the water that you might be drinking to sort of to help you in the water is, you know, a lubricant for a lot of your body parts and stuff like that. Water, they say, oh yeah, water makes up like, what, 70% of the human body, they say. Well, the reason for that is because your body has so many moving parts at all times that water has to constantly be surrounding these parts in order for these parts to be able to move, right? Imagine if you didn't put oil in a car engine, right? Granted, oil is a much smaller percentage of a car engine than it is water is in your body. But water facilitates the movement of your body, but it also facilitates the chemical reactions of your body. It facilitates the absorption of materials by the individual parts of your body. That's something that oil has nothing to do with, right? The gasoline system that fuels your car is a completely separate system to the oil system, whereas in your body, the oil and gasoline would be kind of a mixture, kind of like a two-stroke engine, right? A two-stroke engine needs to have an oil and gas mixture because the oil and the gas are being fed together into the system. So the fuel has to lubricate as it combusts in order to produce a reaction. So, but as I said, you know, you need to have enough sodium in your body, otherwise you're going to dry out, have dry throat, you know, dry mouth, your lips will get cracked, your cuticles on your nails will start peeling up, things like that. And so your body, you know, you die. Absolutely, you would die if you were to eat like a block of pure sodium, right? And so your body needs it to be in the form of sodium chloride. Adding that chlorine in there makes it sodium chloride, which makes it so that your body can actually get sodium without having to worry about literally having a fireball in your stomach, because the sodium is violently reacting with the hydrogen, dihydrogen monoxide in your stomach. By the way, I guess I just said water in a very chemical way. So, yep. there's chemical change, reactivity, flammability. I'm not really sure these are going to be all that helpful to you, and I'm trying to skip things that are kind of unnecessary in these lessons. But I digress. I think that will be where we stop today's lesson. We have talked about a little bit of chemical and physical properties and such like that, and we've kind of given you a basic breakdown of how matter works and what things constitute matter. So please, if you have any questions, talk to the Twitter handles, Shinrai Sensei 15 on Twitter, at Shinrai Sensei 15, and you can also leave them in the comment section. I'll try to keep up with stuff. Please, I hope to God that I'm doing a good enough job, and I will be making an announcement in another video that I'm going to be posting shortly after this one. I hope that you guys will be following me along on this journey still, and I am thankful for all of you for spending the time to watch this.